Welcome to another educational video on physics. Today we are going to discuss the different forms in which you can write down Coulomb's law in electricity. Now we are going to look into the local form of Coulomb's law, otherwise known as Gauss's law for electricity, which is the differential form. And we will also look into the non-local form of Coulomb's law, which is the integral form. And in order to start, we will have to, like always, start with the mathematical description of Coulomb's law. Let me start with the differential form. It's one of the four Maxwell's equations. So if I consider the case of free space, then I can write down the first of Maxwell's four equations in differential form in this way. It just tells us that the divergence of the electric field vector is given by the electric charge density, which we show here by rho, divided by epsilon naught, which is the permittivity of free space. So the electric field, which is general, a function of space and time, it can change in space and change in time. So it's a field vector. It is generated in the static case by a charge density, which itself can be, in general, a function of space and time. So this is the electric charge density. And this electric charge density, if you have a region in space in which you have some distribution of charge, you can generally show it by the electric charge density. Now, this electric charge density can take different forms depending on the nature of the problem. You might have a linear charge density, a surface charge density, a volume charge density, or just the distribution of point charges. What the first equation of Maxwell's four equations states is that this is the source of the electric field. To be more exact, the divergence of the electric field that is a result of the charge density is simply given by the charge density divided by epsilon naught. Remember, these are functions of space and time. So if I have a charge distribution in some region in space, I can actually talk about the divergence of the electric field as a result of that charge distribution. Now, this is obviously the differential form of Gauss's law, or some may call it Coulomb's law. I would prefer to name it Coulomb's law for historical reasons, but Gauss was a brilliant mathematician which taught us how to, convert the divergence of a field vector to the integral of its normal component over a surface that encloses that field vector. We'll look into that when we want to derive the integral form of Coulomb's law. All right, so let us first write down the integral form of Coulomb's law so that we would have a clear picture, and then we will try to, start with one form and end up with the other form. So if this is the differential form, the integral form of Coulomb's law would be given in this form here. So we have the integral, the surface integral, closed surface integral of the normal component of my electric field, which I can show by the dot product between an element of surface, which we call d sigma, by the electric field. That gives me the total charge enclosed within that surface divided by epsilon. Now, this follows Gauss's law or Gauss's theorem. And I'll show you in a minute how this works. So let's say I have, I don't know, in a region of space, I have some charge distribution. It can have any form. And I want to understand how the electric field behaves from this charge distribution that is generated by this charge distribution. All I need to do is to, consider a imaginary closed surface. So remember, this is in 3 dimensions, so we have an imaginary closed surface S, and let's say this closed surface S actually contains within it, in general, the charge distribution, and the volume of this closed surface, I would probably like to show it by V. So V is a finite volume in which within it there's some charge distribution. And let us assume that the total charge inside this closed surface is given by this QENC. QENC stands for charge enclosed. All right. So this is Gauss's law, or in other words, the integral form of Coulomb's law. Now I want to show you that these two forms are actually equivalent. So I will start with the differential form and I'll work my way to the integral form. So this is how we would do it. I would take the volume integral of both sides of this equation. So I'll write this as the volume integral of divergence of E over some element of volume, which I'll show by d tau. That would be given, according to this first equation, according to the differential form, by rho over epsilon naught rho over epsilon naught times d tau. All right. Now, according to Gauss's theorem, the divergence of any well-behaved vector field, such as the electric field, over some volume is exactly equal to the surface integral of the normal component of that electric field over the surface, right? So that normal component, I can show it by E dot n hat d sigma, or just simply, I can show it by E dot d sigma. E dot d sigma. This is over the closed surface, and this is over the volume that this surface encloses. And so if you want to, find out what this d sigma and d tau are, it's quite simple here. So for instance, if I, break down this surface into infinitesimal little elements of area, let's consider the area of every single infinitesimal piece to be d sigma, and the area vector, according to the definition for closed surfaces, is always pointing outwards from the surface, and it's perpendicular to the surface. So the area vector of d sigma would be pointing, let's say, in this direction, right? Now, on the other hand, this d tau, of course, is the volume element that this surface encloses, and that can be, generally shown by this little differential cube here, which has a volume d tau. All right. Okay. So this is given by Gauss's theorem in vector analysis. Okay, in a separate video, I will prove to you how you get from the divergence of a vector field, its integral over some finite region in space, to the enclosed surface integral of that vector field, right? So assuming we apply Gauss's theorem to this electric field, this is the form that it would take. Or in other words, it will just be the dot product between E and d sigma over the surface area S. Now, on the other hand, the right-hand side of this equation can be worked out. I know that the permittivity of free space is a constant, so I can bring it outside the integral and look into the volume integral of my charge density. So the volume integral over some region in space, some volume in space, the volume integral of the charge density over some region in space would give me nothing but the total charge enclosed within that volume. So if I have some volume charge density, let's say distribution within this volume here, then the total charge enclosed within it would be nothing but the volume integral of this charge density. In other words, the definition of, let's say, volume charge density is charge per unit volume. And if I rearrange this, I can easily say that the little element of charge within some finite, infinitesimally small element of space would be given by rho d tau. And if I take the integral of both sides over that volume, that would give me the total charge. So let's say this is the total charge. So in other words, I end up with the total charge being nothing but the volume integral of the charge density over some region in space. Okay, so we'll keep this and we'll apply it to this integral here. And I know that within the surface S, in other words, inside this volume, I have some amount of charge, which I would show it by Q enclosed just to indicate that the charge is completely inside the surface. So the left-hand side takes this form. The right-hand side would take this form, Q enclosed divided by epsilon naught, and that would lead us to the integral form of Gauss's law. In other words, we would have the integral, surface integral of E dot d sigma. That would give me total charge enclosed by S divided by epsilon. And this is the integral form of Gauss's law or Coulomb's law. If you reverse these operations, you can start with the integral form and end up with the differential form. So this was a very quick demonstration of how you can actually relate two different forms of Gauss's law, or the first of Maxwell's equations, or what I would like to call it, Coulomb's law in electrodynamics. I hope you learned something out of this very short video. If you have any questions, please leave it in the comment section. And please don't forget to subscribe to my channel. And I would see you all next time. Until then, take care of yourselves and bye-bye.